All right, in this section, we are going to talk about buffers. Buffers or buffered solutions are special mixtures that are resistant to pH changes, even when small amounts of a strong acid or base are added. Buffers are able to resist large pH changes because they contain both an acidic and a basic component. The acidic component in the buffer will neutralize any added base, and the basic component in the buffer will neutralize any added acid. Buffers are prepared in one of two ways: by mixing a weak acid and a salt containing that acid's conjugate base, or by mixing a weak base and a salt containing that base's conjugate acid. As an example, consider a buffer solution composed of HF and NaF. The acidic component is HF. HF aids in the neutralization of any strong base that is added to the buffer solution. The basic component is the fluoride ion, F-, which comes from the sodium fluoride. It aids in the neutralization of any strong acid that is added to the buffer. Let's assume initially equal concentrations of HF and F- in the buffer, and then examine what happens when the base KOH is added to it. So here's first our equal concentrations of HF and F-. So first, the added KOH breaks down to create K+ and OH- ions. Without a buffer, this would lower the pOH and raise the pH. Without a buffer, the solution would become more basic. Here is how the buffer keeps the pH and pOH of the solution stable. The HF in the buffer and the OH- react to create F- and H2O, eliminating the extra hydroxide. So some of the HF is used and some F- is produced. The proportions then of HF and F- change. In other words, they're no longer equal, but that is acceptable. The goal of keeping the pOH and the pH stable is achieved. So let's assume we have equal concentrations of HF and F- initially, and see what happens when we add a strong acid. So first, that strong acid dissociates, creating H3O+ ions. Without a buffer, this would lower the pH and the solution would become more acidic. Here's how the buffer keeps the pH of the solution stable. The F- and H3O+ react to create HF and water, eliminating the extra hydronium ion. The proportions of HF and F- change. So we consume some of the F- and produce some HF, but that is acceptable. The goal of keeping the pH stable is achieved. We see in this example that the pH of the buffer solution is maintained even after a strong acid or base is added to it. That is the objective of a buffer solution. The concentrations of the components of the buffer change due to the addition of an acid or a base, which you can see reflected by the increase and decrease shown here, but the pH and the pOH do not. Buffer capacity. Two important characteristics of buffers include 1, its resistance to change in pH, and 2, its buffer capacity. Buffer capacity is the amount of acid or base the buffer can neutralize before the pH begins to change. In other words, how much can the buffer handle? We showed in the previous example that adding strong base or strong acid would change the concentrations, but not the pH or pOH. But at some point, that will happen, okay? And when that pH begins to change depends on the amount of acid and base component ions present in the buffer solution, and that's just known as the buffer capacity. Okay, so buffer A has equimolar amounts of acetic acid and sodium acetate for a total volume of 1 liter. Buffer B has equimolar accounts of acetic acid and sodium acetate for a total volume of 1 liter. The difference is in the concentrations of those acids and bases. The above two buffer solutions have the same hydroxide ion concentration and then therefore the same pH. The pH depends on the Ka and the relative concentration of acid and base only. This can be seen in the following calculation. So just as a reminder, the dissociation of acetic acid in water produces the acetate ion and the hydronium ion. Okay, and so at equilibrium, Ka is the hydronium ion concentration times the acetate ion concentration over the acetic acid concentration. But because these two concentrations are the same in both buffer A and B, this ratio is 1. So the Ka is equal to hydronium ion concentration. So even though these buffer solutions have different concentrations of acids and bases relative to each other, they have the same pH because they have the same hydronium ion concentration equal to the Ka. Even though they have the same pH, the buffering capacity will be higher for buffer A because it contains a greater number of moles of acetic acid and sodium acetate. Buffer A will be able to neutralize more moles of any acid or base that is added. The Henderson-Hasselback equation provides a way to directly determine the pH of a buffer solution given the concentration of components in the solution and the Ka or Kb of the acid or base. This is a powerful tool. We derive it for acids and their generic salts, and then bases and their generic salts on the next two slides for generic acids and bases based on the following dissociation equations. The first for a weak acid in water, the second for a weak base in water. All right, here's the derivation of the Henderson-Hasselback equation for an acid and its salt. Here's the dissociation of a weak acid in water to form hydronium ions and this conjugate base. Ka for the dissociation of this generic acid HA is given as the concentration of the hydronium times the concentration of the A minus over the concentration of the weak acid. Rearranged slightly just to emphasize the H3O plus in the front and the ratio of the base to the acid. Take the negative log of all terms. So the negative log of the Ka is also known as the pKa. The negative log of the H3O plus is also known as the pH. Then we have minus the log of the A minus, which is the base, divided by the acid. And then I just rearrange to solve for pH. So I get pH is equal to pKa plus the log of the base concentration over the acid concentration. This is a powerful equation that can be used to calculate the pH of any buffer solution if I know the concentration of its components, the concentration of the base and the acid, and the Ka of the acid. All right, here's the derivation of the Henderson-Hasselback equation for a base, B, and its salt, BH+, which is the conjugate acid of the base. So Kb for the dissociation of the base is given, BH+ times OH- concentration over the concentration of the base. Rearranged slightly, just to show the ratio of the acid to the base. Take the minus log of all terms to get pKb equals the minus log of the OH- concentration is the POH, minus the log of B plus or BH plus is the acid over the base. And so POH is the pKb plus the log of the concentration of the acid over the concentration of the base. Of course, then we can find the pH, 14 minus the POH. So this form of the Henderson-Hasselback equation can be used to calculate the pH of any buffer solution given the concentration of its components and the Kb of the base. There are two versions of this equation, one for weak acids and their salts, which is this one here, and the other for weak bases and their salts. Either version of the above can be used to solve for any problem by converting Ka to Kb. Remember that they are related through K water. Product of Ka and Kb is 1 times 10 to the minus 14. Or we could convert POH to pH. 14 minus the POH is the pH. And then we can use either form of the equation. All right, here's example 5 for buffer calculations. What is the pH of a solution containing 0.2 molar acetic acid and 0.3 molar sodium acetate if the Ka of the acetic acid is 1.74 times 10 to the minus 5? All right, this question is actually really similar to everything we did in example problems 1 through 4, where we had either a weak acid or a weak base, and we added a salt that contained a common ion. But in examples 1 through 4, we solved it using the Ka expression, the equilibrium table, solving for X, and so on. In this case, we solve the pH using the Henderson-Hasselback equation without solving for the hydronium ion concentration as we did in part A of those problems. So first, we can identify this as a buffer solution as it's a mixture of a weak acid and its salt with the conjugate ion. So it is, right? Acetic acid is the weak acid, and then the salt contains the acetate. Then we can just substitute the given concentrations of acid and conjugates into the Henderson-Hasselback equation, where pH is equal to pKa plus the log of the base concentration over acid concentration. The acetate ion is the base. It is both the conjugate ion of the acid and the ion of the salt. Since the acid is weak, meaning not very dissociated, the main source of the base is from the salt, sodium acetate. So here's the dissociation equation for the acetic acid to acetate and hydronium ion. Substituting the givens into the Henderson-Hasselback equation, the acid concentration that we're given is 0.2 molar, and the acetate or base concentration is 0.3 molar. And we're given Ka as 1.74 times 10 to the minus 5. So the pH is the pKa, or the minus log of the Ka, plus the log of the base concentration over the acid concentration. That computation gives us a pH of 4.94. Example 6. The pH of a lactic acid solution is 4.30. Calculate the Ka of lactic acid if the lactic acid and lactate ion concentration in the solution are 0.020 molar and 0.073 molar. In this case, they don't give us the formula for the lactic acid or the lactate, but that's okay. We can just use the general dissociation of a weak acid, HA. So this is our acid. In this case, it's the lactic acid, which we're told has a concentration of 0.020, and that dissociates into a base, which in this case is the lactate ion with a concentration of 0.073 molar. So using the Henderson-Hasselback equation, we're going to solve for Ka. We know that pH is 4.30 equals the pKa, or the minus log of the Ka, plus the log of the base, which is the lactate, over the acid, which is the lactic acid concentrations. And then from here, we just have to solve. So I just solve for the log of the Ka, and I get minus 3.74. So log of Ka equals minus 3.74. And then just a reminder that to solve for Ka, we raise both sides 10 to the power of. So that cancels the log, and we get Ka is equal to 10 to the power of minus 3.74, or 1.82 times 10 to the minus 4.